Okay, I'll start. Thank you very much for coming to my talk. My name is Ilya Sutskever-A. I'm from the University of Toronto. And I will tell you about some work I've done on understanding budget perceptrons slightly better. So I'll start with the last slide, with a summary and conclusion. So there are two algorithms which are budget perceptrons, which I care about in this talk. They are the forgetron and the randomized budget perceptron. And in this talk, my main result showing that both algorithms are following the gradient of an L2 regularized hinge loss on the points in which they make mistakes, plus some noise. And then using this observation, we can prove their regret bounds using online convex programming results relatively easily without using heavy math. So that's it. So now let's start. I'll tell you a bit about the perceptrons. So the perceptron algorithm is an algorithm for binary classification. Give it an example X, which is a vector in high dimensional space. It has a weight vector W, and it classifies things based on the sign of the inner product. And whenever it makes a mistake, it updates their sign. It updates the weights using the delta rule. In other words, it takes the truth minus predictions times the vector and adds it. So if there is no mistake, there is no update. And as a result, we get that W is a linear combination of the vectors in which a mistake was made. So if the data is low dimensional, then we may want a nonlinear classifier, because we can come up with problems for which a linear classifier is not satisfying. So then it's possible to use the kernel perceptron, which is exactly like the perceptron, except that we classify phi of x instead of x. But otherwise, conceptually, it's exactly the same. We say that P, the prediction, is the sign of the inner product between phi of x and W, the weight vector. And then we update the weights exactly as usual. We say that W equals W plus truth minus prediction, which is the delta rule times phi of x. So if we make no mistake, we make no update. And as before, W is the linear combination, but this time of phi of x. So conceptually, it's very simple. I expect this is something we should all be familiar with. But if we use the kernel perceptron, then we get a nonlinear decision boundary, which is good whenever we have low-dimensional data. As far as I know, for high-dimensional data, nonlinearities become less important because it's pretty difficult for high-dimensional data to be nonlinearly separable. So the problem, so the kernel perceptron algorithm is very nice because it's online. It has all the perceptron learning. It has all the perceptron guarantees. It's easy to implement. But the bad thing about it is that computing these inner products, W, inner product phi of x, takes linear time in a number of errors. So if you make many errors during training, we expect this inner product will become slow, and it will slow down learning. So for example, if you make 10,000 errors, it will become pretty much invisibly slow. So here is a picture which illustrates the situation. The kernel perceptron maintains W, which is a set of vector, which is linear combinations of phi of the mistakes it made. And these bars represent the signs of the coefficients in the linear combination. And when the perceptron has a fixed learning rate, as it always does, the magnitude of these coefficients is always the same, but the sign may differ. Now, the problem so if you make too many mistakes, our learning becomes slow, and this is a problem. And there are a number of solutions which are all based on the following rough idea. It says that let's say that we put a strict upper bound on the number of vectors we will maintain. So let's say we will carry not more than B vectors. So B stands for the budget. If we carry B vectors, then we know that our algorithm will not become extremely slow. There is a bound on how slow it will be. And in order to implement it, the philosophy goes like this. Suppose we run our perceptron and suddenly we make a mistake. So if we want to add a vector to our set of vectors we carry, we must first remove a vector. So that's it. So that's how we maintain the budget. And there are 4 algorithms, as far as I know, for doing perceptrons on a budget. And I will care about 2 of them which have formal guarantees. And these are the forgetron and the randomized budget perceptron. So I'll explain these algorithms right now. They're very simple. So this is a simplified version of the forgetron. So in order to remove a vector, we take a weight vector and we scale it down. And then we remove the oldest vector. And then we add the vector in which we make a mistake. So pictorially, here is the weight vector we maintain. These are the mistakes on which we made, but notice that here x ends on a b and not on m because we don't carry more than b vectors. So the first vector, which is, so here let x1 be the vector on which you made the last mistake. So you'll have a high coefficient. x2 will have a smaller coefficient because every time we scale the vector down. x3 will have an even smaller coefficient in absolute value. And the last vector will have a tiny coefficient if we make enough of, if we make a sufficient amount of the scaling downs. So here, the hope is that if this is small enough, then by removing it, we don't hurt performance a lot. And at the same time, if we scale things down only slightly, we don't hurt performance too much either. So that's the idea here. And this thing can be proved to work nearly as well as the best, as the best fixed hyperplane of a norm of certain size. So this is the simplified forgetron. So I'll go over it again. We scale the vector down, then we remove the vector with then we remove the x vector with the smallest weight, and then we add the new vector on which we make the mistake. So now, this was the first algorithm which we care about. The second algorithm which we care about is the randomized budget perceptron, which says the following. Suppose you want to add a vector to yours. Suppose we run the perceptron and we made a mistake. So now we want to add a vector to a set. So we need to remove something. What do we remove? We remove something at random. So it's really simple. Just pick a vector, remove it at random, done. And now add a vector. So this is the randomized budget perceptron. So here's how it looks like. We have the points in which we make our mistakes, and we carry only b of them, and we just pick one at random and we remove it. Very simple. So now both of these algorithms have regret bounds, which relate the number of errors, the total number of errors they make, to the hinge loss of a fixed linear classifier plus some error terms. And I will state the regret bounds which I was able to prove using my technique, which are very similar. They're almost the same as the original regret bounds, just the technique is a bit different. So the number of errors for the forgetron, or the expected number of errors for the randomized budget perceptron, is less than some constant of the hinge loss of some vector, where the hinge loss is the hinge loss on all the examples we've seen, plus some constant times the budget, where we are competitive against vectors of order square root, whose norm is of order square root of b for the randomized budget perceptron, and for vectors of order square root of b of order whose norm is of order square root of b over log b for the forgetron, which is also the same as in the original results. And now, so far I told you existing stuff. I didn't say anything new yet. Everything I said so far was old results. Now here is the main observation which relates these two algorithms, and which makes it conceptually easy to prove the regret bounds. So both algorithms, here is if you forget everything, this is the slide you should remember. Both algorithms follow the gradient of the hinge loss of the errors plus L2 regularization. Both algorithms follow the gradient plus different types of noise. Specifically, the forgetron has small deterministic noise in the gradient, and the randomized budget perceptron has zero mean noise in the gradient, which is very structured, and which is nothing like Gaussian noise, for example. But it doesn't matter. This observation, so this shows us, in some sense, where these algorithms are coming from. Just different, we simply add different noise to L2 regularized hinge losses. That's the first thing. The second thing, so here we are doing gradient descent on very different loss functions, but we only update the parameter whenever we make a mistake. If we don't make a mistake, we simply ignore the point. So here's how both algorithms look like. We run the perceptron, and whenever we make a mistake, we compute the gradient, we update our weight by following the gradient of this function, plus some kind of noise. That's it. And now I will show you how using this observation, we can prove their regret bounds using Zinkovich theorem. So let's look at the simplified forgetron. So the forgetron, when I say simplified forgetron, I mean that the constant factor by which we scale things down is always the same. We just pick some number and we scale a vector down by some number. So this operation is what you get when you follow the gradient of an L2 regularization, because the gradient of an L2 regularization grows as your vector grows. This is simple. This is small deterministic noise, because we expect that the constant by which we scale things down, if it's small enough and b is large enough, then this thing is going to be pretty small. So this will be small deterministic noise. Now this term right here is the gradient of the hinge loss whenever we make a mistake. So whenever we make a mistake, the gradient of the hinge loss looks like this. That's it. So therefore, this justifies the fact that the forgetron is in fact an instance of this algorithm. Now let's go to the randomized budget perceptron. In the randomized budget perceptron, we also have two updates. The first update is remove a support vector from the support set at random, and the second update is incorporating the new point. So the new point is incorporated is also the gradient of the hinge loss, so that's easy. It's exactly like before. If you take the hinge loss on the point at which you make a mistake and we differentiate it, we will get this kind of gradient. But now, what I claim, which is also very simple, is that if we remove a support vector at random, this is like we remove w divided by b plus some noise. So basically, here is what I claim. When we do the randomized budget perceptron is following the gradient of the hinge loss plus an L2 regularization plus some noise. Here is the reason. When we remove a support vector at random, you could ask yourself, what's the average thing we remove? And the average thing we remove can be seen to be equal to w over b. So if w is the sum of b terms, and we pick a term at random, then the expected value of a term is just w over b. Because the expectation is the sum over all possibilities times the probability. And the sum over all these things is just w. So this is it. This is the second important observation. I mean, it's not complicated at all. It's simple. I want it to be understood by everyone. That in the randomized budget perceptron, when we remove a support vector at random, we are following an unbiased estimate of the gradient of an L2 regularization. So that's it. This is the justification for the observation. And now, I will outline the way in which I apply Zinkevich theorem and a version of it in order to get regret bounds. So Zinkevich theorem tells us that if we have a sequence of functions and we do gradient descent, then the performance of our algorithm will be nearly as good as the performance of any fixed point in hindsight. So in other words, if we do online gradient descent on these functions Lm on our errors, then the total loss we will experience will be comparable to the loss of any fixed weight that may know all the examples even after they were given. So if we apply it, we get a bound that looks like this. We can say that our algorithm, which is what I said right now, the performance of our algorithm. So by the way, I should point out, in case you forgot, that Lm is the hinge loss of the mth example with Wm plus L2 regularization. So the performance of our algorithm on this function is less than the performance of anything fixed plus some term which is called the regret. Yes?
Can you say what is the formal statement of the Zinkevich theorem?
I can. I have a slide for that. It's a bit long, but how much time do I have?
5 minutes.
5 minutes.
Maybe 6.
You know? OK, fine. That's good. So I'll spend 1 minute on that. Zinkevich theorem says that if you have a sequence of convex functions, and if we do online gradient descent on these functions, then the loss of our and let the x's be the sequence of gradient points which we do. Then the total loss which our algorithm experiences is less than the loss of anything fixed in advance, plus some error term, which depends on various parameters. But basically, it says that if you do online learning where you don't know the sequence of functions, you can relate your performance to the performance of something which knows all the functions in advance, but is not allowed to change on every function. So I want to outline how I apply Zinkevich theorem to the forgetron. So I should just say one thing. In the forgetron, we have errors in the gradient. But it's very easy to take the proof of Zinkevich theorem and to run it with errors in the gradient, and you get an extra term in the regret. But it's very easy. It works out just fine. So what we get is the following. By applying Zinkevich theorem, we get that the loss of our algorithm. So OK, here's what I'll do. I will take Zinkevich theorem, and I'll apply it only on the functions, on the hinge losses on which I make a mistake. If I don't make a mistake, I don't update my parameters. I ignore these functions. Now, I take the sum. The performance of my algorithm is smaller than the performance of anything fixed, which is not too large. And now this is a parameter. I don't tell you how large the vector is allowed to be. Now, because this is the hinge loss of on a mistake then it's bigger than 1. This is L2 regularized hinge loss, and if it makes a mistake, it's bigger than 1. Therefore, the sum over the mistakes is going to be bigger than the number of the mistakes. This is a famous trick. If you've seen these examples where the hinge loss is bigger than the 0-1 loss, that's exactly what's going on. So the number of mistakes is less than the total L2 regularized hinge loss. And now we get that this is less than something which depends on the L2 regularized hinge loss of a competing vector. And we will get a factor of m on the right-hand side. So we just need to tweak the parameters to make sure that the constant factor next to m here is smaller than 1. If the constant factor next to m here is smaller than 1, then we can pull m to this side, and we get that m times some constant is less than the hinge loss of w plus some other terms. And that's it. And this is what we do for the forgetron. Now for the randomized budget perceptron, we do something slightly differently, which is a trick from a paper by Flaxman, Taman Kalai, and McMahon, where we say the following. Here, with the randomized budget perceptron, it's slightly more complicated because we have noise, and the set of vectors which make the mistakes is different every time. So what they do is they do is a really nice trick. They say, let us add noise to the functions, so that doing gradient descent on the noisy functions is exactly like doing gradient descent on the normal functions plus noise. And then we apply Zinkovich theorem on the noisy functions and average, and it all works out. And finally, I will say one last point. That we can take, so Zinkovich theorem also has a variant for tracking. In other words, Zinkovich theorem is not only competitive against a fixed vector, but it's also competitive against a sequence of slowly changing vectors. So if you say, I want my algorithm to perform as well as something which changes. As long as the change is not very large and the learning rate is not very small, then we will also get regret bound. And the proof is also very easy. We just take Zinkovich theorem and look at the proof, and we add some terms, and it all works out. No thinking is required. We just do a straightforward derivation. And by using the tracking variant, we can get bounds for both the forgetron and the randomized budget perceptron, which are competitive not against a single fixed hypothesis, but against a sequence of slowly changing hypotheses. And I will finish here. Thank you.
Any questions? I have one question.
Yes.
So what prevents you from applying your technique to more sophisticated budget algorithms?
Probably, so it depends on the algorithm. But as long if
You have applied only to the forgetron, this budget perception thing. You know, the big algorithms, let's say second order algorithms, where the budget is even more important because they are more expensive in terms of the number of current supervectors.
So I'm not familiar with these algorithms, but as long as you can express the second order algorithm as something which is where you follow the gradient of something nice, like an L2 regularization or something else which we know, and we can say, well, what we really do is this gradient plus some noise, whether it is deterministic or stochastic, then we can definitely apply this technique.
So it has to be a gradient descent
Yes.
kind of
So as long as you can relate your algorithm to a gradient descent scheme, you can immediately apply this idea. And you can have both stochastic and deterministic approximations. Zinkovich theorem is very robust.
Any more questions? Comments? So let's thank the speaker.